So welcome to module 4, network models and introduction to Ethernet. So what is a network model or what is an OSI model? The model is basically a segregation of different layers. This is an abstract concept. This is not a physical segregation. This is a logical segregation of various parts of a communication protocol stack. So I have used so many words here: protocol stack, segregation, layers. So basically, I'll go back to our UART concept. So what does the UART say? The UART says that TX has to be separate line, RX has to be a separate line. You have to send a start bit, you have to send a stop bit, and your data can be 8 bits. So that is a physical restriction or a logical restriction of sending data over a serial network, UART. And what does the RS485 or what does RS232 say? It says that voltage level has to be so and so. It says that you have to use so and so pairs of cables. You have to use a balanced signal. Or in the case of an RS485, you have to use in the case of an RS232, you have to use the unbalanced signal. You can use a 4 wire. So these are restrictions or these are standards on the physical medium, on the encoding of data, on the transmission technique. So all these standards, the number of cables, the medium used, the encoding used, comes in the physical layer. So that is what physical is. So all our discussions, earlier discussions, UART, RS232, all these are taking care of the physical aspects of data encoding or start bit transmission technique, whether you're using start bit or stop bit, baseband or broadband, whether you're using modulation. So all these techniques, whether you're frequency modulating, whether you are using Manchester encoding, whether you are using NRSDI encoding. So all these encoding techniques, what bit and what symbols are being used, this comes under the scope of physical. So this physical link is the fundamental, most basic link of a communication. So all the other protocols or all the other layers basically works over a physical layer. The physical is the foundation. It's like a basement of a building. So the strength of a communication, the bandwidth or the quality depends on the physical implementation. The physical is the base. Now over the physical is the data link. Now this is where frames come. So in a physical structure, you don't talk about frames. You don't talk about how data is structured. Address should be sent first. These things you don't talk about in a physical layer. That part of the thing is defined by a data link layer. The data link layer refers to a set of protocols or standards which defines how frames are developed or what addresses are, how addresses are, 8-bit address or MAC address, or how like do you address a device, whether the address is restricted to 8-bit 255 up to 0 to 255, or whether the address is unique in a like MAC. So this addressing, framing, and logical distinction between various devices, nodes, all these, whether the frame has been reached correctly or whether you need to retransmit the frame, the error checking, and who can who can transmit when. So all these things comes in the data link layer. So Modbus RTU comes in the data link layer. We have discussed in the last module. So up to now we have only seen physical layer and Modbus layer. So the Modbus RTU works over a physical layer. See, without the physical layer, the RTU cannot work because this does not define the voltage levels, that does not define the data encoding or the baseband bit. all these things. It only defines how the frame should be made. Frame should have an address, should have so and so function code, and it should have so and so error checking codes. That is what is defined in the data link. And in the address, how the data is shared, that is also defined. But the physical layer takes care of all the start bit, stop bit, clock synchronization, data encoding, baseband, broadband techniques, all the number of wires connection. This is basically think about the physical aspects of the transmission. And the data link talks about the framing. Now, over the data link layer, there is another layer called network. So the network comes into picture when there is routing involved. By routing, what I mean is, suppose you are having a Modbus network, and suppose there is another Modbus network which is not connected to your Modbus network. So these two networks can be thought of two different networks. This is like you're having a Modbus network here for collecting data from your like energy meters, sem meters. You are having a sem meter network. You are sending collecting weekly readings and sending to the load dispatch center. So that is a separate Modbus network or whatever, RS485 multi drop network for the sem data. Maybe it is not using Modbus, it is using DLMS. So DLMS is another example of multi drop data link protocol. So DLMS. So maybe it is using DLMS. So uh, that is one network. And maybe here over here you're having another solar inverter connected to your PC, or you're having water meters there. So water meter network, you're having two networks. So when two networks needs to communicate with each other, that is when a routing comes into picture. That is when routing comes, that is dividing a network into sub networks, or dividing. You're having more than one path. You're having more than one path to a device. So from point A to point B, it is straightforward. But whether from point A to point C, whether you have to go directly or via point B. So that is when network comes into picture. Network comes into picture when you have physically separate networks, or when you have multiple paths to take. So that is when a network layer comes into picture. And until that point, everything works in the data link layer, completely fine. But when you have more than one valid path to from point A to point B, you can either go through that path, or you can go through this path. So you have to optimize for your path length, or you are having two different networks that have to talk to each other. That is when network layer comes into picture. Network layer, for example, like the internet protocol, IP. The IP network layer takes care of routing. So the routing is deciding which path to take. And subnet traffic control. Subnet traffic means you're having two different networks, and network traffic of one subnet should not pass to the traffic of the second subnet. So that is subnet traffic control. And frame fragmentation. Suppose you are having a frame which is larger than the frame that is the larger than a frame that is allowed by the data link layer. So suppose the data link layer is having a restriction, you can only send 1 KB at a time in one frame. Suppose the data link has having that restriction, but your upper level protocol is getting rid of that restriction by using a frame fragmentation method. So it will use a higher level protocol for fragmenting the frames and overcome the limitation of the lower layer. So that is for frame fragmentation. And it will also use some other physical address in addition to the data link address. It will use a network level address like a IP address. So that is a distinction between a MAC address and an IP address. The MAC address is a data link address, and the IP address is a network link address, network level address. So when a MAC address has to be universally unique, but an IP address can be should only be unique in a subnet or in a particular network. So the higher the um, protocol, the more features or the more problems it solves, and that is the network layer. Basically, the network layer is the IP layer. So nowadays, network layer internet protocol has become so advanced and so popular that only example I can come up with is an IP. And your network devices like uh, Ethernet switches. Ethernet switches work in the data link layer basically. It's a poor example of network switch. Oh, so your router works in the network layer. So it is looking at IP address and it is deciding whether it has to go in the port number one or port number two, or whether I have to send it to a particular gateway, or whether I have to, uh, whether the packet has expired the time to leave, whether I have to drop the packet. So this network switch that router decides, router has basically an IP table and decides all these things because router works in the network layer. But an Ethernet switch works in the data link layer. It only looks at MAC address. But nowadays, the industrial standard is such that you cannot exclusively get a data link device. All switches nowadays have some form of IP filtering and network level protocols. So nowadays, even switches are not particularly limited to data link layer, because switches, even your switches can have VLANs, have network level packet filtering. So that the OSI model clearly doesn't apply to such modern devices, but still you can attempt to segregate them. So basically, your router works in a network layer, and your programs in a PC. This is software layer. Your your all your programs that run in your computer uses the TCP layer to send and receive data, because the physical structure takes care of the encoding. The frames take care of addressing between local devices. The packets take care of routing. If there is multiple paths, it takes care of subnet traffic. It takes care of frame fragmentation. The TCP takes care of acknowledgement. Means suppose frame is dropped. Suppose you're sending some data and the IP time gets dropped due to some error. There is nothing in these three layers that will allow for retransmission. Basically, uh, there is nothing defined in these three protocol layers that allows for retransmission of data. That is what transport layer solves. It allows for data retransmission, data acknowledgement. It allows for flow control. In flow control, what I mean is, suppose you are having a 10 Mbps connection to a particular server, but the server does not support a 10 Mbps connection. You are flooding it with data, but the server is only able to receive 1 Mbps. So whatever excess data that you're sending is ultimately dropped. So by keeping on sending 10 Mbps of data, you're ultimately wasting your bandwidth. So that is when a TCP protocol, it throttles the speed of your connection. So it takes care of data flow throttling. It takes care of message acknowledgement. It takes care of all these section multiplexing, multiple section expiry, all these things. So each protocol layer is solving some particular part of a problem, particular part of a communication problem, the overall picture. So that is what you should keep in mind. You should not specify, if you're not understanding, what you have to take from this is that each layer in a communication protocol, each layer adds complexity, adds more complex protocols, adds more complex features, and each layer is solving a particular problem. The physical layer is solving the problem of the physical communication between devices. The data link layer is solving the problem of the framing of the addressing, local addressing in the local subnet, and the network is taking care of the problem of routing. The transport layer is taking the care of the problem of acknowledgement, segmentation, and flow control. So this is the OSI model, open source interconnection model. This is just an abstract model, is a concept. Actual physical devices available in the market operate independent of the OSI model. There are multi-layer devices available nowadays. No like managed switches can work in a data link layer, network layer. Router can work even in a transport layer. So nowadays, advanced devices has become so advanced that routers can work in the transport layer. Switches can work in the network layer. So all these things can be done. But the fundamentals are important to understand the segregation, the specification, means the core concept. Because unless you understand that the router is a network device, it does not make sense that nowadays routers can even work in a transport layer. But the fundamentals you have to get right. That is important for understanding an OSI model. So since this is an introductory class, most of the things that I mention or that I say might not make sense, but in further module or further future uh, sessions that I plan to make, I'll discuss the OSI model in detail. But since this is a heavy subject, this OSI model, understanding the OSI model comes with some prerequisite knowledge. So I can only explain to a certain extent. The only thing that you have to understand is that whatever we have discussed until now was in a physical layer. We are not discussing about network layer. We were not discussing about transport layer, and Modbus RTU works in the data link layer. Now, in the previous module, I was telling that like there was Modbus, other Modbus protocols also, like the Modbus TCP and the Modbus ASCII. So basically, here you can see the Modbus TCP and Modbus RTU that I have said. This TCP you might recognize is the transport layer. The Modbus TCP is the transport layer. So Modbus TCP actually is not in the data link layer; it is in the transport layer because Modbus TCP is implemented over IP protocol. Modbus TCP IP protocol. It is not in the data link layer, but Modbus RTU is in the data link layer. This is a clear distinction. So that is what you have to take from this. Basically, if you're not understanding OSI models, have references I'll attach along with this module. You have to some prerequisite is there for this OSI model to understand. And this is a TCP. This is another network model. It is much simpler. So in this, I like to explain the TCP model is a much more realistic model. Unlike the OSI model, TCP model, the lower level models are the same physical data, but there is a further it is not segregated that much. This is a network model. As internet is a IP. Internet is basically IP, Internet Protocol, and the transport layer is basically TCP, UDP. So these are the most exclusively used protocols in these layers. It's like a monopoly of for these protocols. And the higher level protocols, this HTTP, FTP, are all in the all in the section layer or the application layer. So basically, the twisted pair configuration, optical fiber SFP ports that we use, the coaxial pair configuration, all comes in the physical layer. So what we have discussed was the twisted pair serial communication. The optical fiber can also be used for serial communication using light modulation techniques, which can be covered in a later section. And the coaxial cable can also be used for serial communication. So these what we have discussed up to this point was in the physical layer, and Modbus was in the data link layer, and Ethernet is another important uh, protocol. This IEEE 802.3. Ethernet is another widely used protocol in the data link layer, like the Modbus protocol, but the Modbus was specific to RTU devices. That is why it did not get industrial recognition. But Ethernet is widely used not just in substation but all over the world for the implementation of internet. So Ethernet and internet are not the same. Don't confuse Ethernet with internet. Internet is a higher level layer. Internet basically takes you from one network to another network. It is a network of networks. But Ethernet is like a local area LAN. Ethernet basically implements the LAN. It does not have an IP protocol, but it is the local LAN for you. Ethernet is a local LAN. So getting to know about Ethernet, at least some basics is important. So you might have seen this RJ45 cabling. in your substation being used. So when you see an RJ45 cable, a beginner might say think that it is universal. It is universal in the sense that if it is RJ45, it is Ethernet. That is a misconception. The Ethernet is has been developing from so long that even Ethernet is having inside Ethernet lot of different uh, speed classifications like 10-bit Ethernet, 100 megabits Ethernet, 1000 megabits Ethernet. So these are separate uh, protocols in its own right that together is called an Ethernet. So which uses the same cable. So the cabling and the connector is the same for all these, but they are physically separate standards. So they are logically very different standards, and the cabling is the same. So the when you in your substation when you connect when you're crimping an RJ45 connector, or maybe you're relay to a network switch, you might be thinking that this is an Ethernet LAN connection. But the thing that you have to take from this is that Ethernet is not a simple protocol, it's a collection of various data link and physical link protocols. And a 10-bit, for example, I'll say a 10 megabit Ethernet uses only one pair. So here, a pair, twisted pair is like this is a twisted pair. This white orange and orange is a twisted pair. Blue and blue white is a twisted pair. Brown and brown. These are four twisted pairs. There are four twisted pairs in a Ethernet jack. So the 10 Mbps Ethernet only uses two of the pairs. I think one and two. I don't remember correctly, but 10 Mbps Ethernet. So suppose you are crimping your Ethernet. Suppose you are crimping, making crimping, and you get it right. You get only these two right. You get only these two right. All the others you did not check for continuity and it was broken. And you connected these two devices. You will still get internet. Sorry, you will still get Ethernet because Ethernet has an internal auto negotiation feature. Means it will try first for 1000 Mbps connection. If it fails, fall back to 100 Mbps. If it fails, fall back to legacy 10 Mbps connection. So even if you crimp these two cables correctly, you think that you might be having an Ethernet connection. You might ping the relay and you might say, okay, it is getting pinged. But that might be following a legacy system. That is what you have to take from this presentation, from this module. The base you have to get right, that even though it is getting pinged, if the relay is getting pinged, but you have fundamentally missed the crimping. Because of auto negotiation, you will not understand whether it is running in a 10 unless you open your network card and specifically look for it. You will not understand whether the link is 1 GB. This 100 Mbps link is also called gigabit Ethernet, and 100 Mbps internet is also called fast Ethernet. So this is fast Ethernet, also written as FE. So your Ethernet switch ports will be like FE port. They'll not say 100 Mbps or they'll not say 100 base T4. These are protocol standard names, but the switch manufacturers will not specify these. They specify FE port. They will specify gigabit Ethernet port. They'll say like this. So this is gigabit Ethernet port. But even if you use a gigabit Ethernet port, you've not done the crimping correctly, it might fall back to 100 Mbps. And then the relay might ping, but the goose might not work. The relay might ping, but it will not report in SCADA. So these things can happen. It was 100. The bandwidth required for a goose to work is considerable. So it might work in 100 Mbps. It might not work in a 100 Mbps connection. And because there is auto negotiation inbuilt to Ethernet, you might not know the difference. If 100 Mbps fails, it might fall back to 100 Mbps. Sorry, 10 Mbps. Because 10 Mbps uses only two pairs, and 100 Mbps uses this uses one pair, and 100 Mbps uses two pair, and gigabit Ethernet uses all four pairs. So if you have crimped correctly, and if your switch supports gigabit Ethernet, and most switches used in a substation supports gigabit Ethernet. So if you have crimped correctly, by default it will work in a gigabit Ethernet configuration. It will use all four pairs, and even if one of the pair is wrong, it will fall back to a 100 Mbps connection. and then your goose might not work, your shadow might not work, or it will work with latency, considerable latency. So these are things that you have to take care when creating an RJ45. And then again, there is a crossover, two types of connection: crossover connection and straight through connection. If you are swapping these one and two cables with three and six cables, if you are swapping them, see in this configuration, in this picture that that it's shown here, basically you can see the green and green white was 1 and 2 here, but here it is in 3, it is in 3 and 6. So internally in this cable, this green and green white got swapped with pins 3 and 6. So this is an example of a crossover cable. So if without ethernet, without a switch, without a ethernet switch, suppose you are connecting a relay to a laptop, you need a crossover cable. That is basically it. If you are using a crossover cable, you can connect two Ethernet devices together without a switch. But nowadays the NIC card in your computer, in your laptop or in your CPU is so advanced that it can automatically reconfigure the pins on its own. So even if you wire a straight through cable to a relay, directly to a relay, suppose you connect the laptop directly through a to a relay, it will still work because of the card in your computer is so advanced that it will reconfigure the pins on its own. It is part of auto negotiation. But older computers does not, the NIC cards need not do so. All network interface cards in your computer might not do that, but all modern manufacturers generally keep that. Or legacy laptops which are running Windows XP and all might not recognize a new relay unless you use a crossover cable. This crossover cable. If you are connecting directly to the relay, that is, all Ethernet switches supports both crossover cable and straight through cables. So that is one more thing that you have to take care when you're wiring Ethernet. So this base T, base X, all these things I'll explain. T stands for twisted pair. So and F stands for fiber optic. So if a Ethernet switch is having 1000 base T, that means that is a twisted pair RJ45 port. If a Ethernet switch is having 1000 base F, that is a fiber port. So that is how you understand the specifications. So when you order a gigabit Ethernet switch with a 1000 base T port, that is a LAN switch. When you order a gigabit Ethernet switch with a 1000 base F port, that is a fiber Ethernet switch, Ethernet fiber switch. And the connect again, when it comes to fiber, the connector is different: SC connector, ST connector, and LC connector. So the connector might also be different. And then X stands for extended. X basically means that you're using all the pairs. X basically means that you're using all the pairs, and all the pairs works in full duplex mode. That is what X means. Full duplex means all pairs can work bidirectionally. That is what X means. And 4 means you are using all four pairs. So normally 1000 base T uses only two pairs. So the 100 base T4 uses all four pairs. So even in 100 even in fast Ethernet, there are further classifications. You want to read that reference I have kept for IEEE 802.3, and this is the Ethernet works in the data and physical link layer. So Ethernet basically works in these two layers, data link and physical. It does not work in the network layer. So in the data link layer, Ethernet is having MAC ID, MAC address between devices. And in the physical layer, it is having physical coding sublayer, medium attachment, and PMD, physical medium dependent. So these three are little more advanced. So I'll only cover examples of these. I'll not go into the base like entire 100% scope of these particular layers. The physical layer further subdivided into coding sublayer, medium attachment, and layer and medium dependent. So coding sublayer is basically taking care of scrambling and encoding. Medium attachment is taking care of symbols, means what represents the positive +1, what represents the 0. So this medium attachment taking care of that, and coding sublayer taking care of scrambling and encoding, and PMD layer is the physical line driver that connects to your optical cable or your twisted pair. And auto negotiation is a part of Ethernet that automatically tries all the configurations and chooses the best one. That is a part of your NIC card that automatically configures your Ethernet port to the correct or to the most higher supported Ethernet standard. Suppose you are connecting a 10 megabits LAN cable, 10 megabits device to your laptop. The laptop is a gigabit Ethernet port. It automatically senses that the device connected is not a gigabit Ethernet device. It will try a fast Ethernet configuration. It will find that the fast Ethernet also does not work, and it will automatically roll back to a 10 Mbps legacy connection. So that is what is auto negotiation. So that is also part of a Ethernet standard. It is also part of a physical layer. So that are the physical layer is further subdivided into these four categories. So an example of PCS, I'll show an example of PCS. Going to the whiteboard. So PCS is a physical coding layer. So in 10 Mbps connections, this is called a Manchester encoding. That means 0 is represented 0 is represented like this, and 1 is represented with inverted pulse. So 1 will be represented. So suppose this is 0 and 1 will be represented like this, and 1 will be an inverted pulse. So this is the starting of a pulse, and it will be represented with a 0, and an inverted pulse will be representing a 1. So that is Manchester encoding. So again, if you need to send a 1, you need to again invert inverted pulse. And if you need to send a 1, you have to send a normal pulse. Means again you need to send a 0 after this, you will send a normal pulse. So it will be like this. This is what is a Manchester encoding is. Means a normal pulse represents 0, inverted pulse represents a 1. And then there is a one more encoding called NRZI, and that is non return to 0 inverted. That is a different type of encoding. This is used in 100 Mbps Ethernet, and in this 0 is represented by no change, 1 is represented by a change from high to low or low to high. So how you send 0011? You'll send one cycle, you'll send one cycle without any change, you'll send one more cycle without any change, and then you will change the level, that is representing a 1. You will change the level again, that is representing a 1. So this is 0011. Suppose you need to send 1001, change in level, you will change level, this is representing a 1. The edge represents the 1, and the absence of an edge represents the 0. So here there is a change in level, that is representing 1, and in the next clock cycle there is no change in level, representing a 0. Again one more clock cycle without any change, representing a 0, and the next clock cycle it is changing. So this represents 1001. So when this waveform, by sending the waveform like this encoding is called NRZI. NRZI, non-return to 0 inverted. But the problem with NRZI, if your data is having too many zeros, your data that it will be flat for almost the signal, the physical signal will be almost without any transitions for majority of the duration. So what will happen? You cannot recover clock from this. So Ethernet is asynchronous. We are not sending separate clock. Ethernet is asynchronous, so you need to recover the clock from the data itself. But if you are sending too much zeros consecutively, you're not able to recover the clock from this area. So what it does is there is something called 4-bit 5-bit encoding. This is in the PMA layer, not in the PCS layer. So again I told there is a PCS layer and PMA layer. So this encoding is taking 4B 5B encoding is taken care in the PMA layer. It is responsible for changing a continuous streams of 0 to a continuous streams of 1, and the PCS layer takes care of the individual symbols, when it should be a 0, when it should be a 1. That is taken care of in this layer, in this particular layer. But the PCS layer, sorry, the PMA layer takes care of the encoding. So what it basically does is it divides the data into 4-bit nibbles. So basically, if you have a long data, like suppose like this, it is divided into 4-bit nibbles like this. That is why 4-bit comes here. And it changes it into 5-bit. It changes it into 5-bit nibbles, such that it inserts a 1 somewhere, so such that there is not a continuous stream of zeros. Suppose for here 1 2 3 4 5 6, 6 zeros are coming consecutively. So when you divide your data into 4 bits and insert one more 1 here and there, so there is a table for this one. It is not randomly you are not inserting. There is a lookup table of 4 bit to 5 bits, so that you can, it is a reversible process. When you're inserting a 1 here and there, at the receiving end the receiver is also knowing that you are inserted a bit. So this is a lookup table for 4 bit 5 bit lookup table for interchanging the data, so that ultimately when you're sending using this NRZI method, there is no consecutive zeros in your transmission data, so that you can recover the clock. So these layers work together to recover the clock and maintain synchronism. If you're not understanding, you don't need to get into details of all these things. Basically, what you need to understand is the physical layer takes care of the encoding, takes care of the clock recovery, takes care of auto negotiation, so that if a higher speed is not achievable, it automatically downgrades the port to a lower layer, and the data link layer takes care of the MAC address. So your network switch works in the data link layer, and your IP device works in the network layer, and the gateway also works in the IP layer. And suppose the gateway is a protocol gateway, it works in the transport layer. For example, a 61850 device gateway, 61850 gateway, which converts from 61850 to 104. It is a protocol gateway, not a network gateway. So the protocol gateway works in the transport layer. A network gateway works in the network layer like a router. So these are the distinction between devices. Switch works in the data layer, router works in the network layer, gateway works in the transport layer, and your programs work in the section layer. Programs like a browser and programs like YouTube, all these things, application programs and web interfaces works in the section layer. So that is the distinction. And uh, going on to moving on to the next slide. This is a summary of all the basic Ethernet standards that are actually practically used right now. So the 10 based is a legacy system using Manchester encoding that I discussed. It is used as LAN because it is a legacy protocol. It is used for in the rarest of rare cases like wake up of LAN or power saving mode. All these when all the other Ethernet standards have failed. That is when the port rolls back to 110 base T. And 10 base T1 is used in automotive industry like the CAN bus used in IoT devices. uh, it's a direct rival to the CAN bus, and it is also works similarly to Modbus also. And 100 base T1, 100 base TX, these are what are used in our normal D-Link switches. So when a D-Link switch, you are purchasing a D-Link 8-port switch, that is a 100 base T1 or TX device. It is not a gigabit Ethernet switch. So suppose your station switch has failed, or one of your Ethernet switches in your station has failed. You're replacing it with a D-Link switch. So D-Link switch is a 100 base device. It is not a gigabit Ethernet device. It is not a 1000 base device. It's a 100 base device. So ultimately, when you're connecting multiple relays to your D-Link switch, which should be in fact Ethernet managed Ethernet switch, but it has failed and you're using a D-Link switch. What happens if that relays will report to SCADA? It will show significant latency. It will either stop completely or it will report with significant latency. Packets will drop. There is no sufficient bandwidth for goosing. 100 base T does not provide sufficient bandwidth for goosing reliably and for client RCBs to report to their client. So when you're connecting relays in D-Link switch, you have to keep in mind there is no sufficient bandwidth for any of you can take DR, you can extract all those things you can do, but there is no sufficient bandwidth for multicasting. There is no sufficient bandwidth for MMS. There is no sufficient bandwidth for master client, that RCB, report control blocks, to function. You have to connect it to a managed Ethernet switch with 100 base T. With span, this 100 base T managed switches are having spanning tree protocols which can avoid loops in the network. But this D-Link switch does not have any such protocols, because it will not detect loops, and it will not have a spanning tree algorithm. Your D-Link switches are maximum 1000, worth 1000 or 2000, but your Ethernet switch will have all those protocols. Your Ethernet switch is actually running a Linux based routing program inside, which takes care of all these things. And each port is independent of the other. Means the fact that you're using one port at full 100 MB 1 Gbps does not limit the capability of the adjacent port. But the D-Link switch might not be like that. The overall D-Link switch can only handle a 100 base connection. Means the fact that you're using one device at 100 Mbps might limit other ports. I'm not saying it will absolutely, but it might depending on the model of the D-Link switch that you're using, model of the switch that you're using. I'm saying D-Link switch, but I think it is understandable. Switches that are not industrials, not adapted for industry, but for the home network. Basically, switches that come in pocket size, home network with an adapter. These switches are basically 100 base devices without for use in home, not for use in industries. They cannot be used in a like protocol intensive network. And gigabit is the 2.5 GB they are actually mostly only there in your STM ports, STM16 ports. In your ULDC or telecom panel, these ports might be there, but it might not be there in your relay, or might not be there in your Ethernet switch. So these higher end ports are only available in your STH or ULDC panels, because they are having considerable. This 2.5 Gbps is actually, I think, if I'm correct, STM16. This is an XTM16, I think. So this port. So these ports are having different bandwidth. Each ports are having different bandwidth. It automatically rolls back to the highest supported. Suppose you're connecting your 10 Gbps port with a 100 base device. It automatically rolls back to the mutually agreed bandwidth. So that is what you have to take care. So in this module, we have covered network layers and Ethernet. So since this is only a basic uh, introductory module, I not discuss the integrities of Ethernet. Only the base things that a substation engineer should keep in mind while making an Ethernet local area connection in their station, while connecting relays to networks. So the base is what you have to take. If you're not familiar with the previous protocols that I have discussed, like data link, physical layer, PCS, PMA, that is absolutely fine. Just keep in mind that this such layers exist. Even if you're not understanding, the data link layer is the MAC layer, or the media access control layer, and just understand that the MAC is different from the IP address. Why IP address has to be cannot be why cannot be unique, and why MAC has to be universally unique, and all these integrities. And this is an example of the protocol stack. So basically, upper level protocols. So the what happens in when the data is there, the upper level protocol, the TCP protocol, transport layer, encapsulates the data with its own header, and it passes the data to a lower layer. So the IP layer again adds its own header, encapsulates the TCP. Now the data for the IP header is the entire TCP frame. The IP header encapsulates all the data, and then it passes to the lower layer. Lower layer is MAC layer, the data link layer. It encapsulates all the data again with its own header and passes it down to the physical layer. The physical layer is having a sequence of bits for starting the data transmission, a sequence of bits for ending the data transmission, and an encoding like a Manchester encoding or their NRZI encoding, and then they're having some scrambling. Maybe they're having multi level scrambling. Maybe they're having 4B 5B encoding. So these physical protocols or physical encoding might be there in the physical layer. So it encodes all the data, the TCP header, the MAC header, the IP header. The physical layer encapsulates all of the above protocols. So that is when the receiver is getting the data, it first unpacks the physical layer, then it unpacks the data layer and gives to the network layer, then it unpacks the IP layer and gives to the TCP header, TCP layer. TCP layer unpacks the data and gives to the application layer. So that is how the Ethernet works, or the OSI model works. So that is what we have discussed in this module. Thank you.